do what they need to do later. All right, so this is recording now. So now, can you guys see the screen?
Yeah, I got it.
Yeah, we can.
Sweet. And you can see me drawing and everything like that?
Yeah,
sure.
Sweet. All right. So what we are going to talk about is we're going to finish up talking about the acidity trends that I didn't want to cover last time that we met, mostly because I think I threw a ton of information at you and I didn't want to overwhelm you with a lot of information. I wanted you guys to be able to process what was going on with acids and bases. So now that you've had plenty of time to digest the beginning of acids and bases and this idea of only acids donate, bases accept, we're really only caring about the acids. Now we can start talking about, okay, we're going to talk about what makes an acid stronger versus another one. How can we make acid stronger? So I need to pull up my reference. I think it's this one. Yeah, there we go. Whoops, not that. Oh, that's good. I can move that. All right. Acidity trends. So what we are going to be talking about is the whole name of the game that we are trying to do is we're trying to increase acidity. So that's what everything that we're about to talk about is primarily centered around. It's this idea about increasing acidity. And in order to do that, to increase acidity, we must, or the better way of saying it is, I can't say that. We want to decrease the effective negative charge on the conjugate base. Have we done this together? Maybe a little bit? Can't remember if we did or not, but it's a good review.
I don't know if we did it.
I think we did the inductive effect together, but it'll be good to go through the rest of them. Cool. So this is what the basis of everything that we're talking about is, right? So we're talking about decreasing the effective negative charge on the conjugate base. Well, why? Why do we want to do that? Well, if we remember that we have this setup going on about HA plus B goes to A minus plus HB plus, right? This is our setup that we were talking about with Bronsted and Lowry. And we talked about how that the acid will donate over the hydrogen and the base will pick it up. But then this acid can go, this conjugate base can steal back that proton, right? And so the question that we asked ourselves is HA really an acid? Because if HA gives up its proton and it becomes HA plus A minus, right? It gives it up, but then it immediately becomes HA again. Did it really donate a proton? Did it really do what it was supposed to do? And so the definition of an acid, if you remember, is that acids donate. So if in the end, it just kind of stole it back, did it really donate? Yes. Yes, it did. It is still an acid. It's just a very bad acid. So HA is a weak acid because the conjugate base is so strong. And this is the basis of what the acidity trends are all about, is that we're going to be decreasing the negative charge, missed that word, negative charge on the conjugate base, because by doing that, we're going to make the conjugate base weaker, which then makes it so that way it's not stealing that proton back, so we're more likely to donate, which means that the acid is stronger. So to summarize everything that we just said is that we're going to decrease the negative charge on the conjugate base which makes the conjugate base weaker. And another way of saying weaker is just saying more stable, which in turn makes the acid stronger. And this is the basis of the trends. This is everything that we care about. This is everything that it's going to be, is this sentence in red. Decrease the effective negative charge on the conjugate base, which makes the conjugate base weaker, which is the same thing as saying making it more stable, which is in turn going to make the acid stronger. With me so far kind of sort of makes sense. If you want, at the end of the acid and base lecture, we went on 9/18, we went through the same thing again. So feel free to go and take a look at that, and it will kind of explain everything that we care about. Cool. What this does is it comes up with a measure. Is that we're measuring, and this is the kind of funky thing about acids, is that we're measuring the strength of the acid based on the strength, or I should say by the stability of the base. And so this is a really common sentence that you'll see in textbooks, different stuff like this. Cool. Sweet. All right, so with all of that sorted out, we can now finally talk about the acidity trends and start talking about it. And remember, we're going to be talking about it in terms of decreasing that negative charge. All right. Well, the first, we only talked about inductive effects, right? We didn't talk about the rest of them, right? I'm not crazy. Okay, all right. I just needed to check again. That's a terrible color. All right, we are going to be talking about, first one is charge. All right. So what I'm going to tell you is that the more positive the species or the atom or the molecule, the more acidic. And so by saying more positive is the same thing as saying less negative. So once again, that plays back to the idea of less negative charge on the conjugate base, more stable, stronger acid. And we can see this with a couple of examples. Here we have like OH minus versus H2O versus hydronium ion. And if we wanted, we could take a look at the pKa values, and we could say that this is not even an acid, doesn't even have a pKa value. The pKa of water is 14, and the pKa of hydronium ion is negative 1.7. But look at that change. This is a difference of 10 to the 15.7, right? Am I crazy? I think that's how math works. So what we're talking about here is a huge, huge change in acidity. So we're talking about something that's almost 100 quadrillion times stronger just by adding a positive charge. So if you have something that's a positive charge, you're going to be bumping that acidity up really, really, really high. Just want to get another thing as well. There it is. Likewise, I just want to show you another kind of set of these is if we take a look at NH2 minus, the ammonide ion, I believe is what it's called. We have the amine, and we have the ammonium ion. Once again, not even an acid cannot donate. Negatively charged species generally do not donate a second proton. Usually they have to be pretty inorganic. We have 38, and then we have 9.2. So again, this is a difference between 10 to the 26 times stronger. So we're talking about an increase in strength larger than Avogadro's number. So immense, immense, immense change, right? Huge, massive, okay? So by adding that positive charge, we make it super acidic. I think this makes sense. I don't think we really need to beat this bush anymore. The second trend has to do with the role of the atom. And so this is divided into two parts, is that across the periodic table, so going left to right, periodic table, acidity increases with electronegativity, which my shorthand is E/N. And so if we wanted to write this out as well, we could see that we have methane versus ammonia versus water versus hydrofluoric acid. And again, what you see is that as you go to the more electronegative atom, like fluorine, which if we wanted to write out our electronegativities, we see that this is 2.5, 3.0, 3.4, 4.0. That what you can see is that as electronegativity goes up, as we go across the periodic table, we are increasing acidity. So if we wanted to write in our periodic table, we are increasing acidity as we go this way. And the question is, well, why? Well, the reason why, and this would probably be a question that's more on Shia's exam than Poulos. Poulos doesn't really go into theory as much as Shia does, is that electronegativity is a measure of how hungry you are for electrons. So if you're more hungry, if you're more electronegative, then you are happy with a negative charge. So a high electronegativity means a more stable anion. And remember, that's the goal of increasing acidity, is that we want to make the conjugate base more stable. So if the anion, the negative charge, is on a stable atom, it's totally fine. It's happy to give up the proton. It doesn't mind at all. And it will happily get rid of it and then move on with its day. Does this make sense? Kind of, sort of, pretty straightforward, kind of. We're going to do a bit of practice after as well. Likewise, acidity, as we go down the periodic table, acidity increases with size. So comparing within our halogen column, we see that HF, let me do this in colors to stay consistent. We have HF versus HCl versus HBr versus HI. And what we see with our nice pKa's that you should all have memorized is 3.2, -8, -9. Yep. Have them more memorized than I do. Is that as the size increases, acidity also increases. And the reason for that is because there's more space, there's more volume. So a bigger atom is able to hold on to that negative charge that negative charge is able to be distributed over a larger volume, and it's able to uh, be able to um, be a little bit more stable. I guess that's the way to say that. I need to put my phone away because I'm getting distracted. Does this make sense? Okay, so this is why even though fluorine is the most electronegative atom out there, iodine has the highest uh, peak, or is the most acidic, because it is a big, huge atom. Like, if here's the size of fluorine, if that's fluorine, here's iodine. Like, this thing is like massive, like it's huge. Okay, so that's what we're talking about. How do we feel about this? Good? Cool. Let's do a little bit of practice, shall we? So what I want you to do is I want you to rank these molecules in increasing acidity. Let me give these some good labels. And based on the two trends that we've learned so far, we should be able to identify what's going on, right? So what's the first rule? Well, the first rule is that we're talking about charge, right? So negative is worse than neutral, which is worse than positive, right? And then our second rule is talking about the atom itself. And we're primarily talking about the periodic table. So what I'm going to tell you is that on your exam, you won't have to worry about comparing going diagonal. So you won't ever have to compare like nitrogen and sulfur. It's talking a little bit too much about, well, sulfur's, you know, or, phosphorus and oxygen. Well, oxygen is technically more electronegative, but phosphorus is bigger. So like, which one plays more? You won't have to deal with that. You'll primarily only be talking about going across one row or down a column. So you won't have to worry about doing both at the same time. And so what we know is that going across is more acidic and going down is more acidic. So we can kind of factor this in both ways. And remember that these are kind of written in order of importance. So what we can do first is we can find all of our positive molecules, and we can be like, oh, okay, that's going to be our more acidic compound. So I would take a look at all my atoms, and the first thing that I do, and by the way, if I'm going too fast, please tell me, is I like to see what's the same. Well, in all of these molecules, I have these same 3 carbons. So I'm not going to be comparing 3 carbons. So I can pretty much kind of write those out of my head. And the reason why I say that is because we only care about where there are point differences, where there's one change that we're able to compare. If there's multiple changes, it gets a little bit too complicated, and then we have to start, talking about experimental data and, a whole bunch of different things. But point differences we can tell. So who wants to give me what they think is the most acidic, hands down?
E.
I would say E, right? E is totally most acidic. Well, how do I know? It has that nice positive charge right there. All the other ones are either neutral or they're negative. And so based on my first rule, positive wins. Followed, I say, okay, I have no more positive molecules left. So now let's take a look at all the neutral molecules. Well, I have 1, 2, 3 neutral molecules, right? Oh, well, now I have to rank these. So I go down to my second rule. And I say that, okay, I'm comparing oxygen, nitrogen, and a carbon, right? So I know that based on my rule that fluorine is more acidic than oxygen, which is more acidic than nitrogen, which is more acidic than carbon. So who wants to give me an idea of what they think the order of the next set of molecules would be? I would say something like A, then B, then F, right? A is more acidic than B, which is more acidic than F, right? And that makes sense. Oxygen is more electronegative than nitrogen, which is more electronegative than carbon. So this is how the kind of the logic plays out. And so now that I'm finished with all my neutral molecules, I can put a good X right through that. And now I can focus on all my negative molecules. Oh, well, I have 2 of those. I have C and D. And so I then go to my second rule. My second rule says, oh, okay, we have,
Quick question, Gabe.
yeah.
On on option F, what's the minus next to the carbon?
That is on a minus. That's me highlighting the carbon that's right there.
Okay, so you're comparing the O to the N to the carbon.
Exactly. Yep.
Cool, thanks.
And so what I'd say is that oxygen is more electronegative than nitrogen. So go C, and then it would go D. Does this make sense? So this is the kind of logic that you really have to be playing with yourself, is that you just go through what the rule says. The rule says that positive is best first. We'll go through all your positive molecules, then go through all your neutral molecules, then go through all your negative molecules. Um, God, sorry, my phone's blowing up. I might have to take a phone call, but we'll see. If we do, we'll take a 15-minute break. Cool. So let's do another spot of practice, shall we? And I'll give you guys time to kind of figure it out on your own. And I'm going to give you as much time as you should take on your exam so you can practice thinking about these things.
So do you just compare it to the first element? So O and O.
So good question. So a lot of you might be seeing something like the salt that's going on here, and you're like, well, that's not what we practiced up above. But don't forget, we know that what does sodium or chlorine act as? Sodium and chlorine and lithium, all these are countercharges, right? So what we're really talking about is O minus paired with a +1 charge. So even though the molecule itself might be neutral, the atom might be charged. All right. So this should be probably a little bit more time than you should spend on your exam. But we're doing practice, so it's all set. So based on our charges and our rules and everything like that, I can go through and I know that this is going to have a negative charge. This is neutral. This is neutral. And that this is going to have a positive charge because this chlorine has a negative charge. And then same thing with this carbon. This lithium has a positive charge, which means that this carbon must have a negative charge. Okay.
Why is the SH and the OH neutral? Because isn't H 1 plus?
So it's a good question. So the reason is because what the OH and the SH are doing is this is a covalent bond versus this is an ionic bond. So here they're sharing the electrons in between themselves. So neither one of them has a charge really. Versus what's going on here is that they both have a full charge, but they're so strong of ions that they cancel each other out. Does that kind of sort of make sense?
Yeah, but wouldn't the NHNA also be covalent?
Yep. So for the NHNA, what we have going on is that we have one covalent bond to I'm going to draw it like this. We have one covalent bond, but then we have a negative charge going on here, and this is the covalent bond, but then this is our ionic bond.
Oh, okay, got it. Thank you.
No problem. Good question. How do we feel about this? Good? Does this kind of sort of make sense? Another thing that you'll see in about 4 weeks is we're going to start talking about partial charges. So technically this oxygen has a partial negative charge and this hydrogen has a partial positive charge. So this is again bringing this idea that covalent bonds, you're sharing charges, you're not really producing full charges, but we'll talk about that later in the semester. We're not really discussing that now. Cool. So let me give these some labels just so that way we're all on the same page. So we'll call that A, B, C, D, E, and F. And so what's my first rule? My first rule is positive, right? So how many positive molecules do I have? I have one, so I know that that's going to be most acidic. Then I go to all my neutral molecules, which is OH and SH, and I say, okay, well, which one is stronger? Well, SH is a larger atom, so this would be a stronger acid than OH. And then finally, I go to all my negative molecules and I say, okay, oxygen is better than nitrogen, which is better than carbon. All right. And so these, it's kind of, they're just puzzles. And that's all Orgo is it's just tons and tons and tons of puzzles over and over and over again. The question is, well, what if I reversed the thought process and I said, well, which is the most basic molecule out there? Well, the most basic is the opposite of the most acidic. So I would just take the opposite of my ranking. And so we can say that E is the most acidic and that F is the most basic. And so we can just reverse all of our arrows to get the opposite of the answer that we're looking for. So really common ways of asking the same question is, what's the weakest base? Well, if you're asking what the weakest base is, the weakest base is the same thing as saying the strongest acid, right? So they're opposites of each other. So if you're being asked what's the weakest base, we're essentially saying what's the strongest acid. Well, what if they say what is the weakest acid? Well, the weakest acid is the strongest base, and so we're just reversing our thought process. That's all it is. Same thing. What if it says the most stable base? Well, the most stable base is the same thing as saying the strongest acid, right? because weak things are stable. So we're saying the same question. So all different ways of asking the same question in different ways.
I have a quick question.
Sure.
So going back to like ranking the acidity, I get why number or letter E is like the first one, but how come it's not A instead of D?
A instead of, for like number 2.
Yeah.
So the reason why it's D next is, so we have to go and take a look at our first rule. And so we got our positive charges out of the way. We're all set with that. So now we look at our neutral molecules, and SH is neutral versus O conjugated with the sodium ion is O negative and A plus. So A is a negatively charged molecule.
Okay, so what about like F then? Is that negative or is that positive?
Negative charge as well. So if I draw out that molecule for you, what's essentially going on is that we have this carbon with the 2 hydrogens, but then we have this negative charge, which is conjugated with this lithium. So this carbon here has a negative charge.
Okay.
Does that make sense?
Yeah.
Okay. Cool. All right. Any other questions on this? We're going to do more practice as well. So if anything comes up, let me know. I'm happy to discuss more. Cool. Let's go on to the third one. So what colors did I use? Can't even remember. I was doing white. The third one is on resonance. Now, resonance is kind of like the big bad. If there's one thing on exam 1 that students absolutely hate, it's resonance. And then on exam 2, it's isomers. And then exam 3 is usually SN and E. And then the final is just a combination of all of them. We are going to do a, we'll talk about resonance more after we finish the acidity trends. So if it doesn't make sense entirely right now, that's fine. We're going to come back to it and I'll kind of brush up on this again if it doesn't. So resonance. Let me pull up my reference so I make sure I'm talking about this correctly. Resonance is all about decreasing that negative charge by distributing it over a large area. All right. So what I want to show you here is this example. That let's say that we have, I don't know, something like ethanol, because we're college students and we drink, except I don't. So fun fact. And we have phenol, which you should not drink because that will kill you. And the pKa of this is about 15, whereas the pKa of this is about 10. And looks like I have to take a phone call. All right, we're going to take a like 5-minute break at most, all right? I keep getting a call from someone, and apparently they really need to get a hold of me. All right, I will be back very shortly, I promise. All right, sorry for this. All right, I am back. Sorry about that. So, all right. So we were talking about resonance, and resonance is this idea about decreasing that negative charge by distributing it over a large area. So if we take a look at these two different molecules, and let's see what happens when we turn them into their conjugate bases. So we have the conjugate base of ethanol, and we get this ethoxide, and we see that it has that nice big negative charge right on the oxygen. Versus we have the phenol turns into a nice old phenoxide, and a special thing happens. What can happen is that because this carbon here, that guy right there, has a pi system, or in other words, is involved in a double bond himself, he can interact with the lone pair that is on this oxygen. And that's basically what resonance is all about. It's about double bonds and lone pairs jumping around and interacting with each other. And again, if this doesn't necessarily make a ton of sense, that's all right. We're going to talk about resonance more in a little bit. So what's going to happen is that these electrons are going to jump right down, which is going to push this double bond up and move it onto that carbon.
Can you repeat that like whole idea one more time? I'm so lost.
Sure. So what has happened is that because this carbon here, let's call this carbon Carl. So this is Carl. Because Carl is involved in a pi bond or with a double bond, and let me redraw this a little bit better. Because Carl has a double bond right there going on with him, because Carl is in a pi bond and he's attached to this oxygen, both the oxygen and Carl are able to interact with each other. And what happens is that these electrons that are here move down and create a new double bond between Carl and the oxygen. So they create this bond right here, this new double bond going on. So that's what happened to those electrons. But if we look at what happens, if nothing else is affected, then that means that Carl would have 1, 2, 3, 4, 5 bonds, right? And carbons can never have 5 bonds, right? That's way too many electrons. We're breaking the octet rule. So what happens is that the bond between Carl and his neighbor, this carbon in red, Carl's like, hey, bud, can you just like really do me a favor? And can you take the electrons that we share? And can you just like hold on to them for me? And the red carbon's like, sure, I don't mind, as long as you eventually take them back. And Carl never does. Carl's like, no, I'm good. Because I have this double bond with my oxygen pal now. And what this has done is it's gotten rid of this double bond here. And now we kind of have this new system going on. Okay? So once again, just to kind of draw this so that way I don't have all these fancy colors going on, this first resonance form looks like this. And so what I want you to appreciate is this, is that what we've done is we've moved the negative charge from the oxygen onto this carbon, onto this red carbon over here. Does that mean that we've decreased the negative charge on the oxygen? Totally, right? We've decreased it so much now that it's neutral. And so that's going to increase the acidity of this oxygen. Because remember, this is where the negative charge was originally. This is where the proton that gets donated was. So by reducing that negative charge, we're going to increase the acidity. What I want you to know for right now is that phenol has 4 locations where that negative charge can show up. And I'll go through this later and I will explain resonance a little bit more. But what I just want you to know is that just like how that red carbon can pick up that negative charge, there are different locations around the benzene ring that can as well. The one that's at the original red carbon, this one that's 2 carbons over, and then another 2 carbons. So it creates this kind of like T formation going on. And so what I want you to know is that these red dots represent 4 locations where that negative charge existed. So what we've done is we've taken that -1 charge and we've divided it over 4 locations. So now it's like all we have really going on is -1/4 charges. -1/4 all the way around. And we have some dotted lines that go in here, and I will explain what these are later. But the big important thing to know is that we have 4 locations, and so is 1/4 less than the -1 on this ethoxide? Is this true? Totally, right? So we've decreased the negative charge in phenol by distributing it over 4 locations, thus creating -4 charges, okay? And go back to our original rule. Decreasing negative charge means a more stable base, which means a weaker conjugate base, which means a stronger acid. So when we look at the pKa differences between ethanol and phenol, we see that the phenol is 10,000 times weaker purely because it has that resonance.
Wait, the phenol is weaker?
Sorry, stronger. My bad. It's 10,000 times stronger. Whoops.
Okay, thank you.
Don't pay attention to me. I have no idea what I'm talking about. You are all going to fail your exam. So Gabe guarantee. Cool. Does this make sense? Kind of, sort of. Let me throw a wrench into what we're talking about then. All right. Well, we talked about phenol here, and phenol has 4 locations where we can have that negative charge. But let's take a look at a carboxylic acid, for example. A carboxylic acid's conjugate base is a carboxylate. And for reasons that I will explain in a little bit, what I want you to know is that we have this kind of arrow pushing, this kind of electron movement that eventually results in a resonance structure that looks like this, okay? This is what I really want you to know for right now, with some dotted lines in between everything right there. And so what we have going on is we have -1/2 charges. All right. Well, if we compare these things, -1/2 is greater than -1/4, right? Because we're comparing the carboxylic acid versus the phenol, right? So based on our rule, we would say, oh, that means the phenol is more acidic, right? Well, actually, it's not true. The carboxylic acid has a pKa of 4. So why is the carboxylic acid, despite having a greater effective charge, way about 1,000,000 times more acidic than phenol? What do we think? Who has a really good idea? Well, the big thing is I forgot the other bracket. This should be a bracket right there. Is go back to our about the rule that's right above resonance, right? So we said that first rule has to do with charge. Well, all these are talking about negative charge. So that doesn't help us. Then the second rule was about the atom, and this third rule is about resonance. We'll take a look at where these charges are going. These charges are mostly 3/4 of the charges are going on carbons versus 100% of the charges in the carboxylic acid are going on oxygens. So who is better at accepting that negative charge? Oh, oxygen, which is why, despite the charge apparently being bigger, it's still more acidic. So remember that these rules supersede each other. And so this is what acidity trends is all about. It's not enough to just know one trend. You have to go right back up to the beginning to start understanding the end.
Is there a ranking, Gabe, like which acidity comes first at all times, like for the 5 acidity trends?
The order that they're given in is the order that they're most important, is what I would say. And if you take a look, I think at the end of the 918 lecture, I give you a list of pKa's that you should just know off the top of your head. And by memorizing them or being familiar with them, it saves a lot of work for you. And you can take a look at those pKa's and compare it to these trends, and you'll be able to like figure it all out.
Okay. But in general, the charge is always first, then atom, then resonance?
Yep. The order that we're learning them is the order that they contribute most to acidity.
Okay, cool. Thanks.
No problem. All right. So the next one is the inductive effect. And so what the inductive effect is, we're decreasing the negative charge by slurping electron density away from the anion, the negative atom. So let's say that I have these two molecules going on. The first molecule is just a cyclohexanol, which would have a pKa of somewhere around, I don't know, somewhere around like 14.2, I think is what it is. I can't remember. And let's say for this other one, we are putting fluorines on this top carbon at this kind of 12 o'clock position. Let's take a look at what happens. Well, again, when we take the conjugate base of each one, what we notice is that for the cyclohexanol, we have only one location where this negative charge exists. And it's this big, bad, old negative charge. Huge, right there. Boom, a full negative charge ready to smack you right in the face. Versus this fluorinated compound, Can you guys hear me?
Yeah.
Whoa. Why is my audio all messed up? Okay. So for this fluorinated compound, what we notice is that this negative charge has decreased to a baby negative charge. It's small, it's tiny. And what we see is that this negative charge is probably somewhere around 12, somewhere around there, somewhere over there. That is not a negative sign. That's a tilde. That's like a about sign. So don't confuse it. And the reason is, well, why? Well, the reason is that remember that fluorine, I'm getting got a chat. How do I, is that what you were looking for, Clara? Clara.
Yes.
Sweet. That the electronegativity of fluorine is 4, and the electronegativity of oxygen is 3.4. So what this means is that this electron density, this cloud of electrons that's surrounding this oxygen, is slowly being slurped away. It's being sucked away right to the fluorines. It's being taken away from the oxygen and decreasing that negative charge. Now, once again, you decrease that negative charge, it means the base is less likely to take that proton back, which means you're making a more stable conjugate base, which means it's a weaker conjugate base, which means it's a stronger acid. So once again, it all comes first full circle. And what's important to know is that there's two really important portions of this to know. Is that the first portion is that the more what are called electron withdrawing groups which we will abbreviate as EWG, the stronger the acid. And that should make sense, right? That if you add on, here's another 2 fluorines, if we add in another fluorine, if we start really packing this thing close with fluorines, we're going to be dropping that pK even further. So like drop it down to 10 or even 9, or, we can bring it super, super far down. I need to... I think I fixed my headphones. Likewise, what we can say is that the closer the electron withdrawing group to the negative charge, the stronger the acid. Right? And that makes sense. Is that if we're trying to slurp electron density away, that the closer you are, the more of an effect you have. And my general rule of thumb is that only electron withdrawing groups within 3 bonds count as close enough to affect pKa. If they're any further away, generally in my view, they don't really have an effect, or a very negligible one. And so if we take a look at what's going on here, for these fluorines that are flanking on either side, they're within 1, 2, 3 bonds of the oxygen, so they're totally going to have an effect. Same with these ones that are down below. 1, 2, 3, totally going to have an effect. Versus this big old fluorine on the end is 1, 2, 3, 4, 5 bonds away. It's going to have a very small effect, if any effect whatsoever. Does this make sense? Cool. Let's do another spot of practice, because I think it's important to do practice. Who doesn't love practice, right? Practice, practice, practice. I will keep this up there. got an espresso machine at home, or my roommate has one, and it is literally the best thing in the world. Because I'm a big believer in like making my own coffee instead of buying it, and my God, it is so much better. I highly recommend getting one. It's a Mr. Coffee machine. It was $50. It's totally worth it. Um, you can like buy the Monin syrups as well. It makes okay foam as well. So if you wanted like a latte or whatever, totally worth it. Fuck Starbucks. Starbucks doesn't know what it's doing. They also have shitty Wi-Fi, so um, Starbucks can fight me. Um, cool. All right. So once again, when we're going through problems like this, just think about what we've been doing so far. So first is charge. Then we're talking about the atom. Then we're talking about resonance. Then we're talking about induction, right? So it's the same thing that we've been talking about so far. So who has an idea of hands down, no ifs, ands, or buts, what's probably going to be the most acidic molecule?
F.
I would say F, right? Why? Because it has that fantastic positive charge right there. And so what does charge do? Charge decreases acidity by 10 it increases acidity by 10 quadrillion times, right? So of course, F is going to be the most acidic. Well, now we have to look to all of our neutral molecules. So that would be D, E, or C. And so I take a look at this and I say, okay, I have oxygen versus nitrogen, right? So in terms of the atom, who's going to win next? Well, hands down, it's going to be the oxygen, right? But wait, this molecule over here also has an oxygen, I hear you say. And I say that doesn't matter because the acidic molecule or the acidic portion of the molecule is this nitrogen. So yeah, it's resonance stabilized. It has some resonance going on. But just because this nitrogen has, this this, this going on, so does this. So they cancel each other out, you could technically say. And so what are you left with? You're left with a nitrogen versus an oxygen. And who wins? Oxygen. Okay? So once again, you could go through the same, just go down the list of things that we've learned.
So when you say 2 is atom, you're looking at the element, right? The element that's bonded to the C bond or whatever.
Talking about like here?
Well, for number 2, you're looking at the N versus the O, right?
N versus the O. Yep. So the reason why I'm looking at these is because the acidic proton is right there. And so this is the thing that gets donated or not. So we're talking about that atom specifically.
Got it. Thank you.
No problem. And so now we're comparing D and E because these are both neutral molecules. So I can skip charge. Now I go into the atom. Well, they're both nitrogen. So I go to the next one. Oh, resonance. So who has more resonance? Oh, it's E. So of course, E is going to come before D. Finished up all my neutral molecules. So now I can go to my negative ones and I have A versus B. Well, they're both negative, so I go to atom. Well, they're both oxygen, so now I go to resonance. Oh, B has more resonance, so B before A. So it really is. It's just like it's a method of just going through the process over and over and over again. Are there exceptions to the rule? Yes, of course there is. There are instances where what you think might happen kind of gets a little bit screwy. But what I would say is that most of the time it works out, and you generally don't come across those exceptions a lot of the time, especially at this stage in the game. If you take Orgo 3 and 4, come talk to me then. Or if you're one of the bratty Harvard kids that I tutor that's like, but wait, I saw this in some medical journal or whatever. Well, go fuck yourself. I don't really give a fuck. Anyways, next. Sorry, the Harvard kids they get on my nerves a lot because they think they're oh so clever.
I have a quick question.
Sure.
So I think I have a hard time telling which one's neutral and which one's negative. So would you not take the conjugate base of like E to make the nitrogen negative?
So good question. And so I see that's a really common thing for students to try to do, but we have to look at the molecule the way that it's written. And so what we're going to say is that we're just assuming that we're comparing the molecules as they're written, not as their conjugate bases might be. Does that make sense?
So when would you look at the conjugate base? Because sometimes you do that.
You would look at the conjugate base if the question was like, rank the following in terms of base stability.
Okay.
So, or another one would be, yeah, that's pretty much the only question that you would say, okay, let me convert these all to the conjugate base form.
But in Professor Shia's class, she always converts everything to the conjugate and then she compares it.
Yeah.
Yeah, you can totally do that as well. So if we wanted to do that, that's totally fine way of doing it. And so let me just...
Are you just cutting the middle step and saying like, oh, you know it's going to happen at the H, so you're just analyzing the N?
Exactly. So the process that I'm showing you is assuming that these are all the conjugate bases. But if Dr. Shia does it that way, then we can still talk about it the same way. And so if I'm not thinking about it, I believe it gives us the same answer. So let me just rewrite all of our things down below, and we'll just take a look at the way that she does it. Yeah, so what we can do is by taking all of these and then converting them to their conjugate bases in a way. I took this from, obviously these aren't going to essentially work because some of these are already the base and you can't convert this any lower. But the principle is the same, is that we can convert this guy here into the conjugate base, right? And we can convert this guy into the conjugate base. We can convert that guy into the conjugate base. And we can convert this guy into the conjugate base. So just rewriting down below what the new list is like, just so that way we're not confused and everything like that, is here's the new list. Just so that way we're not getting confused and comparing it. So we can do the same thing, the same process going on as what we were doing before and taking a look. Is that, first we're talking about charge, then we're talking about the atom, then we're talking about resonance, and then we're talking about inductive. Right? Well, all of these are negative except for one, right? So what's going to be the one that goes first? E. Followed by, okay, well, now we take a look at the atom and we say we have oxygen, oxygen, oxygen versus nitrogen. Oops, let me label these for us as well. All right. So we, oh, well, that's not E, that's F.
Gabe, just to clarify, F is the most acidic one, right?
Correct. So we're ranking these in terms of, which is most acidic, which is the same way as saying which is the most stable base.
Okay, thank you.
No problem. Same question. So compared with our charge, F is the only neutral thing. We know neutral is more acidic than negative, so we know F is going to go first. Then we take a look and we see we have oxygen, oxygen, oxygen versus nitrogen, nitrogen. And we say, okay, we know that oxygen is going to be better than, oxygen is going to be better than otherwise. The only problem is that I didn't account for this portion of the problem, so we have an overlap going on. So what we can say is that we know that which is better, oxygen or oxygen, they're exactly the same. So we go to resonance, and so we can say that C is better than, which is equal to B, which is better than A, because this just happened to give us the same molecule. Maybe for shits and giggles, what I'll do is I'll put a nice fluorine on there just so that we can talk about the inductive. So now with that idea, well, they're the same molecule, they have the same resonance, but now the fluorine makes this a little bit better. And then finally, B has more resonance than A. And so now we can start comparing our nitrogen molecules. So then E is better than D, which should give us pretty comparable, slightly different list, but that's just because we kind of fiddled around with different things. But as long as you understand how this ranking came about, then you're totally fine. So whether you convert to the conjugate base first or you just leave them the way they are, you'll come out to the same answer. We did not come out to the same answer purely because we had an overlap going on. So it's just going to change the nature of what we're going up. Do we feel good with this? Does this kind of sort of make sense? Cool. Whichever way you do it, just do the one that makes you feel best. It doesn't really matter. Just stay consistent. That's the big thing in organic chemistry. Stay consistent. What I'm going to post in the chat right now Oh, Clara, you work at Starbucks? How could you? You've betrayed me. You may no longer attend my sessions. That's all right. I'll let you stay. Cool. So what I just posted in the chat is some practice for you. I pulled a couple of questions from there, but you should be able to do everything that's in there now. What I will post down, what I will also post, and both of these things will go up on the Google Drive as well. So if you're like, oh, where did that thing go? This is where it's going. That here is the answers. So the first link is the practice problems, and then the second link is the answers to them. Once again, I'll throw them in the Google Drive link. Cool. Last trend, and then we are all set, and then I will explain resonance to you. The last trend is the simplest trend. It is the trend that comes up the least because it is the most specific. And again, it's at the bottom of our 5 acidity trends. So you have to get through everything else and then eventually get to this answer. So it's the one that shows up the least. Or it's the reason, so we can do that. What I will tell you is that the more S character the anion has, the more negative, the less negative it is. And
So
once
Gabe,
again, go ahead.
Professor Shia talks about hybridization. Are these the same thing?
Yep, same thing.
Okay, cool.
And so remember once again that you decrease that negative charge, you make the base more stable. The base is then a weaker base, which makes the acid more stable, stronger. So all ties in together. So what does this mean? Well, let's say that you have, I don't know, you have an alkane versus an alkene versus an alkyne. Well, the pKa's of this are 50, 30 something, 42, not completely wrong number, and 25. Okay. And take a look at what the hybridization is. So for these carbons, the hybridization is as follows. This one is sp3 hybridized. This one is sp2 hybridized. And this one is sp hybridized. So what is going on here is that this carbon is 25% S, 75% P. Likewise, we can say that this carbon is 33% S, 66% P, and that this one is 50-50. So what Mother Nature is telling us is that as you become more and more hybridized, as you get more and more double bonds, as you get more and more electron density around you, you become more acidic. All right? And look at that. This is a difference of 10 to the 25. This is bigger than Avogadro's number. This is a huge number. All right? So by adding a triple bond, you are causing a significant change. But again, it's the one we see least of, or it's the reason we see least of because you have to get through all the other trends first. Does this make sense? It's kind of the most straightforward one. People generally don't really struggle with it. What I will tell you is that these trends are given to you by cardio, the acronym, which is the charge, the role of the atom, resonance, dipole induction, which is just a fancy way of saying the inductive effect, and then finally orbitals. So when you're doing acid trends, you can always be like, oh, what's the cardio? And you can just go through it. So now you should be all set to do those practice problems I gave you. They should make sense. If you have questions, feel free to reach out to me. When we do our thing tomorrow, we'll go through more of those questions. We won't go through the entire thing. Generally, I like to go through practice exams and show you guys what you can expect, which is a little bit better. Cool. Any questions on any of that so far?
Do you go through Shia practice exams or Poulos practice exams?
I have the Poulos exams already, but if people send me Shias, I go through them as well. It's just that it's harder for me to get Shia stuff for whatever reason. So if you have them, send them to me and I will take a look.
Okay, I don't have any, but like if you did have them, would they be on the shared drive?
They would be. Let me reach. Do you know who your TA is by any chance?
Is that the recitation professor?
It should be a student.
I think it's Gwyneth.
Gwyneth.
Yeah.
If you want to just send her an email and be like, hey, do you have any practice exams for Shia? She'll usually just send them to you. I'll check with a student who was in Shia last year. She might end up just having them. If not, I'll check in a couple of places because I know I have them somewhere.
Okay, only if it's allowed. Like I was just wondering. Thank you.
Usually it's fine because we're looking at old exams. If I had the new exam, I would. Would I give it to you? well, because this is recorded, I will say I would not, which I wouldn't anyways, because that would be cheating, and I don't want to get kicked out of school.
Yeah, I don't want to get you in trouble. I was just wondering if it's allowed. Then could we get it?
Yeah, if I can find him, we'll definitely do him. Last year, I don't know if you guys remember, but I did the midnight reviews. So, oh, I guess I should tell you guys now, before we head into resonance, is that tomorrow, so Thursday, is we're not doing 4 to 6 p.m. We're doing 8 to midnight. So it's a nice long 4-hour review. It's the one because your exam is on Friday, right? Yeah. So this is a way for us to just go through all the material, talk about it all, go over problems I see people struggling with, really just kind of blast it out, do all of your studying, and then so that way you can go to bed at midnight and sleep, because that's what people do is they stay up all night and they don't sleep. And if we were in person, this would be in Reed Hall, and I would buy people hot chocolate. I think people remember me doing Gen Chem, and I did that. That was a lot of fun. But you know, needs must. Coronavirus. Cool. All right. Resonance, and then we will be all set for today. Oh, sorry. I need to go to. I haven't done this lesson in a long time, so I have to remember one specific thing. There it is. All right. Resonance structures. So, resonance is all about the delocalization of electrons across pi systems. Whoa, that's a lot of vocab words. What does that all mean? Well, I'll tell you. What this is basically saying is that when you look at a bond, remember that there are electrons that are shared in single bonds, right? These guys are locked in. They are unable to move. You cannot move shared electrons because if one atom tries to give it away, the other one's gonna be like, no, 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 fuck you. They're staying right where they're going, okay? They are staying right here. Versus if you have a double bond, what's happening is that you have your usual shared electrons that are part of the single bond, but then what's interesting is that you have this pi bond, which we write as these little bunny ears. And these electrons here are not really locked in place. Because what's interesting is that they can interact with other pi electrons. And pi electrons can be double bonds or lone pairs. So what's going on is that we have this oxygen also has pi electrons. And what we see going on in this funky way is that the pi electrons that are in these carbons can interact with the pi electrons that are in the oxygen. And so this is what a pi system is. A pi system is just an interaction of pi electrons. Let's repeat that for a second. We know that single bond electrons are locked in place, whereas double bond or lone pair electrons can be shared between multiple different, or can be interact with nearby pi electrons. And when pi electrons interact with each other, they create the pi system. So let's take a look at what happens. Let's say we have, once again, this molecule going on. All I want us to do is I want to label all of the atoms that are involved in a pi system for these different molecules. That's all I want us to do. So we have this enol going on. We have this benzene ring. And then, I don't know, let's talk about our carboxylic acid, for example. Or carboxylate. What I want you to know is that when we're putting dots on all of the atoms that have lone pairs or double bonds. So these carbons are involved in a double bond, and this oxygen has at least one lone pair. This benzene ring, well, this carbon is involved in that double bond. This carbon is involved in that double bond. And this carbon is involved in that double bond. And then for this carboxylate, this oxygen, as we know, has a lone pair. This carbon is involved in a double bond. And this oxygen has at least one lone pair. So the question I want to ask you is, can carbon A interact with oxygen C? Totally. Because A is connected through B, and that B is part of a pi system as well, A, B, and C can all interact with each other. And that's what a pi system is that the interaction of one pi bond with another pi bond. Same thing here. Can all the green carbons interact with all the blue carbons, which interact with the red carbons? Totally, because these carbons are touching and they're both in a pi system. So that means they can interact, which means that all four of these carbons can interact, versus here the red and the blue are touching and they're both in a pi system. So these can interact. And these are in a pi system and also touching. So red, all of the red carbons can interact with all of the green carbons, which can interact with all the blue carbons. All right, so they all line up together. And then, as you can probably guess, because both of these oxygens are touching this carbon, both of these oxygens can interact with each other as well. Does this make sense so far? Yes, kind of, sort of, maybe. So by contrast, what I want to show you is this molecule. Can the two double bonds interact with each other? Well, I'm going to put dots on the carbons that are involved in pi systems. And what we notice is that we have a bridge. We have a break in the continuum. So can green interact with blue? No. Green cannot interact with blue because we have something in the way that is blocking green's pi system from interacting with blue's pi system. All right? This describes two systems. All of these guys up here are what are called conjugated pi systems. Conjugated meaning that they're all of the atoms involved in pi bonds are all able to interact with each other. Versus down here, this is called an isolated pi system. So why am I explaining all of this? The reason is because only conjugated pi systems can interact in resonance forms. Only conjugate structures can undergo resonance. Isolated structures do not undergo resonance. So let's take a look at resonance. Can I move away from this? Do people still need a second? All right. So, what I'm going to tell you is the moves. Resonance moves. These are all your valid resonance moves that you're allowed to do. All right? Let's say that we have any given molecule. I don't know, maybe ours looks like this. And we have one that looks like that. The first valid move that we're allowed to do is the double bond push, also called electron pushing. And what this means is that we're going to take one of these double bonds and we're going to hop over to put it in between our two pi systems. So now what we have going on is now we have a red-blue pi bond or double bond. By the way, if you are struggling to be able to label these with colors and stuff like that, use stars and circles. That'll help you keep everything straight. What this has done is that we can't have the double bond over here stay because that would be way too many bonds on this carbon. So what's going to happen is that this bond is going to move up and land on the terminal carbon in the pi system. And it's going to gain those two electrons. And this is what the double bond push is all about, or electron pushing, is that by moving one double bond, we move another double bond. We're not done yet because we have to look at charges. This carbon here, this one, Debbie. Debbie has lost electrons, right? It's lost 2 full electrons. So Debbie's charge has gone from neutral, losing a full charge, to +1. So Debbie now has a charge of -1 or +1. It was neutral and it lost an electron, so now it's +1. Whereas for Tom, it was originally neutral, but now it's gained an electron, and so it now has a charge of -1. And this is what the electron pushing is all about, is that you move away from something, you gain a positive charge, you move towards something, you gain a negative charge. How do we feel so far? Kind of good enough? Kind of? Okay. Let's take a look at some practice of this. Let me do some labeling. And what I want you to tell me is give me one major resonance form for this molecule. Well, first steps first is to put some colors down and identify all the atoms that are involved in the pi system. Carbons 2 and 3 are interacting with each other because they're both in a pi system and they're adjacent to each other. They're touching. And so what I can do is I can do a double bond push. And what I can say is, I don't know, maybe I want to go away from carbon 1 and push it. Notice what I'm doing. I'm taking the bond that's in between 1 and 2 and pushing it between 2 and 3. And I'm taking the bond between 3 and 4 and pushing it onto 4. Wow, I'm like really struggling here. So what's going to be between carbons 2 and 3 now? Well, it's going to be a double bond. And so what's the charge on carbon 1 now? Well, we're moving away from it. So whenever we move away from something, it's going to gain a positive charge. And whenever we move towards something, it's going to gain a negative charge. How do we feel about our first resonance move, the electron push? Good, kind of. The second move that I want to tell you about, the second valid resonance move that we can do, is called the step down, or it's called the step up, depending on which way you're going. this is probably your most common move that you were ever going to be able to do. And it's really simple. So let's say that we have this going on. Well, what the step up move is that we know that this carbon is involved in a pi system and that this oxygen is involved in a pi system. So what I can do is I can step up these electrons onto the oxygen. And so what this is going to do is that it's going to, we're going to degrade this double bond into a single bond. And we're moving electrons away from this carbon. We're moving it away from Derek. So Derek is losing an electron, which means he's going to be positive. So we can write a good old positive charge right there. And this oxygen here, Henry, well, Henry is gaining an electron, so he's going to be a charge of -1. So that's the step up. The step up is where you take a double bond and you step it up onto an adjacent atom. Step down is just really similar, is where we have an atom that has a lone pair, and we take it and we step it down onto an atom that's involved in a pi system. And so what's going to happen here is now this oxygen on the right is now going to have a double bond with the carbon. We're going to create a double bond. And so this oxygen was originally -1, but it's losing an electron. So now it is neutral because a negative minus a negative is a positive. So it's like we're saying negative plus 1 equals 0. And this carbon over here, this original one, the Derek carbon, was originally +1, but it's gaining an electron, so now it's neutral. So what did we end up doing? Well, we ended up moving this negative charge onto the other carbon, onto the other oxygen, sorry. And so remember how I talked about way back when we were talking about acidity? And I asked you, well, why is carboxylic acid half charges? Well, this is why. Because if we look at what's going on, that this oxygen is bringing the bond down and this one is bringing it up, we have two locations where that negative charge is going. So this is why resonance is stabilizing, is because we're distributing it over a large area. How do we feel about this? Good, kind of good, good, not so good, bad. What do we feel like? Good? Good? Okay. What I'm going to tell you is this, is that resonance is the kind of thing where you can only really get good at it through practice, which sucks. So there is a fantastic PDF in the Google Drive that if you go to the Google Drive, then go to second year, then go to BU Orgo, then go to first semester, and then look for a PDF that's called CH203_5_resonance. .pdf. This thing goes through, Dr. Rubio does an amazing job explaining resonance. So if you want practice, or you want explanations, or you want just another source to go and read something, I highly recommend it. Likewise, I always recommend Mastering Organic Chem. I think he does a great job at kind of dumbing things down. The other one is Leah Forsai. She's an amazing resource. She does a great job on YouTube. So if you have any questions about those, I definitely recommend going to them, because I think the way they do it is just kind of clever. We'll put some, we'll put some grass down. Cool. Any questions so far on anything that we've done? Good. Let me check the chat just to make sure. All right. I believe this is everything that we have for today. So again, oh, what the hell? These don't even erase. Wow. Tomorrow it's going to be 8 to midnight. I will make a post about it. We'll just meet on Zoom, of course. I highly recommend making yourself a cup of hot chocolate or a cup of coffee, just to kind of get that experience of the Gabe tutoring, midnight tutoring in for you. In fact, I'm going to make it a requirement. If you don't drink coffee, make a thing of tea. If you don't do any of those things, don't come. What's the other thing? We're going to go through practice problems. We're going to go through practice exams. I'm going to try to get the Shia ones. If you have questions in the meantime, send them to me. I'm around. This will go up on YouTube. I'm going to try it. Usually it takes like a day to process. I'm going to try to get it done in a couple of hours. So that way it'll be up, hoping by tonight. And then we will be all good, and it'll be, oh my God, so much fun. And then we'll talk about post-exam stuff, and it'll be fun. Cool.
What's your opinion?
Oh, someone just said something, but it sounds really jumbled for me. I think that might have been Clara. Whoever just said whatever you did, throw it in the chat and I'll answer it. Good question. My username for YouTube is, so for the Google Drive, it's tinyurl.com/Gabe Tutoring. And then for YouTube, it's the same thing, but YT for YouTube. I was told that I have to say this as well, is that make sure you like and subscribe, hit that like button, and ring that bell. And all the other bullshit that all the people say. Give it a year. I'll be on like the Instagram like news like video thing. Just wait. Gabe Tutoring will be there. Cool. All right. Have a great night. I will see you all tomorrow. Get fucked. I don't know. Just, as it is. Cool. Goodbye, everyone.
Thank you.
Thank you.
You're welcome.
Thank you, Gabe.
Thank you, Gabe.